Okay, we're going to get into a new topic today, something called improper integrals. This is going to help us get ready for the next big topic, which is going to be Taylor series, Maclaurin series, and sequences of series in general. So this is a really super important thing. You really need to take good notes on this. All right, so we're going to start off. The topic here is improper integrals and integrals to infinity, and I had to put a picture of Buzz Lightyear to make that work. Anyway, infinity and beyond, right? Or integrals and beyond. Why it didn't work. Anyway, here we go. So we're going to go ahead and take a look at an integral we should be able to do, which is 1 over x squared. Remember, we can always rewrite this as 1 to 2 of x to the negative 2 dx. So we're going to get from 1 to 2, we're going to have x to the negative 1 over negative 1 from 1 to 2. And so we get 2 to the negative 1 over negative 1 minus 1 to the negative 1 over negative 1, which is equal to negative 1/2 minus plus 1, so a half. Okay, pretty straightforward, right? Well, let's take a look and see what happens if we do that for any arbitrary upper limit. Okay, so I'm going to do the same thing. My antiderivative will be negative x to the negative 1 from 1 to b, or negative 1 over x, I suppose. I'll write that, negative 1 over x from 1 to b. And so I'm going to plug in b, so I have negative 1 over b minus negative 1, which is equal to negative 1 over b plus 1. I can rewrite that just for fun as b minus 1 over b. Okay, so for any particular upper limit, I have a formula now that's going to tell me the area under the curve from 1 to b of 1 over x squared. Okay, so if I put in 1 to 2, I get 2 minus 1 over 2, which is a half. Okay, so just something to note that we can do here. So for any arbitrary upper limit. All right, so we're going to take this now, and obviously we're going to be looking at integrals to infinity. So let's see what happens next. Here's our picture. Okay, that's 1 over x squared. That's the picture. We just looked from 1 to 2. We looked at that area and decided that area was equal to a half. Now, we're going to look and see what happens as b goes to infinity. Now, this is what we had in the previous slide, and I want to know what's going to happen now as we let b go to infinity. So instead of going from 1 to 2, we're going to let b go from 1 all the way over to the right. Okay, so basically I'm just doing the limit as b goes to infinity of this. Okay, well, what is that? Well, we know that this is 1 over b minus 1 over b, so it's the limit as b goes to infinity of b minus 1 over b. Okay, well, what happens here? These go at the same rate. This is equal to 1. Okay, we can look at that by separating the fraction again if we want. This is 1 minus 1 over b. 1 minus b goes to, 1 over b goes to 0. The limit of b minus 1 over b is equal to 1. Okay, another notation we often use, instead of writing out this kind of cumbersome b go to infinity 1 to b, we just say, for shorthand, 1 to infinity. And that's equal to 1. So here's a strange thing. If we let the limit, if we ask for what is the area underneath the curve 1 over x squared, and we let the limit to the right go to infinity, we actually end up with a finite area. Infinite limits of integration, finite area. Okay, so that should be something perhaps you've never thought about before or seen before, but this area from here on is finite. Okay, so here is the theorem that we're going to be looking at here. Well, this is not a theorem, this is actually a definition. Okay, a function is said to be unbounded, I'll highlight that, near a, if f is unbounded on every open interval of the form a to x or of the form x to a. Okay, so what that means is that on any small region, no matter how small we make it, we can't find a boundary. Okay, suppose f is unbounded near some value a. Okay, then if either of the integrals a to c, okay, that is to say we're going from some unbounded number to a finite number, okay, Or if we look at a finite number to an infinite number, okay, so unbounded to finite or bounded to finite, to infinite, pardon me, if either of these have a finite area, so if they equal something, we say that the integral converges. Otherwise, we say it diverges. All right? Okay. So let's take a look at these two integrals. We're going to decide whether they converge or diverge, and then we're going to go ahead and try to figure out what they are. Okay, so 0 to infinity of e to the negative x dx. Now the way we have to do this is we have to substitute infinity with a number. So this is really the limit as b goes to infinity of 0 to b e to the negative x dx. Okay, so that's the limit as b goes to infinity of, let's see, we're going to have negative e to the negative x from 0 to b. The limit as b goes to infinity of negative e to the negative b minus negative e to the 0. Well, that's simply the limit as b goes to infinity of negative 1 over e to the negative, or sorry, to the positive b now, plus 1. Well, so as b goes to infinity, the denominator goes to infinity, so this entire fraction goes to 0. And that goes to 1. So the area under this curve is also 1. Okay. From 0 to infinity, 1 over e to the negative x is going to infinity as well. Okay. Let's take a look at this one. Now this one on the surface doesn't really look like a problem. We have 0, we have pi over 2, but let's take a look at the graph. Actually use Grapher. Okay, pi over 2 is going to be, let's zoom out a little bit. Okay, 0 to pi over 2. Okay, so pi over 2 is just a little over, so we're in this region here. Hang on a second, what's pi over 2? If I plug in secant, remember, is the reciprocal of cosine. Okay, this is 0 to pi over 2 of 1 over cosine squared of x. Cosine is 0 at pi over 2. This thing is undefined at pi over 2. So we actually have a problem here. We have to approach pi over 2 from the right because this function is undefined at pi over 2. If we look back at the problem again here, we look at the graph, this is pi over 2 right here. So I'm looking at an unbounded region from 0 to pi over 2, but we can only approach pi over 2 from the left. Okay, so we're going to go ahead and have to look at this as, again, we're still going from 0, but we're not going to pi over 2, we're going to b. And we're letting the limit of b go to pi over 2 from the left. Because, again, we cannot plug pi over 2 into the secant. Okay, so we'll go ahead and we'll integrate. All right, the antiderivative of secant squared is tangent. The limit as b goes to pi over 2 from the left is going to be tangent of b minus tangent of 0. B goes to pi over 2 from the left again. Tangent of b is just tangent of b. Tangent of 0 is 0, so we're just looking at what happens to tangent as we go to pi over 2 from the left. This goes to 1. Okay? Because tangent of pi over 2 is 1, it's continuous at pi over 2, tangent is, so we end up with a value of 1. All right? Okay, so this is one of those interesting situations where technically speaking, in order to do this integral, we probably could have just done it without even realizing there was a limit involved, but there is a limit involved, and it's important to recognize that. Okay, so here's another theorem. We're looking at the improper p integrals, is what we'll call this. A and p are real numbers where a is between 0 and infinity, so a is finite and positive, and p is not equal to 1. So this whole thing doesn't apply to the situation where we have 1 over x. Then when p is greater than 1, that is to say when I have 1 over x to a power greater than 1, so x to the 1.5, x to the 2, x to the anything like that, then if I'm asking what's going on between 0 and a finite number, so between 0 and a finite number, this region in here diverges, does not have a finite area. But if I look to a number to the right, the area on the right here converges, has a finite area. For the same kind of situation where I have p less than 1, that is like a p of a half, a p of a quarter, p of 0.237, okay, anything like that as an exponent here, it's exactly opposite. The area to the left converges, and the area to the right diverges, okay? So what that really means, we often use this part right here in practice. If p is greater than 1, then this is a finite area. That's often how this gets applied. Let's look at some examples. All right, we're going to try to integrate this from 0 to 3. And notice, let's take another look at this problem here. On the surface, it doesn't look too bad, except that this is discontinuous. It has a vertical asymptote at x equals 1. Okay, so really what we have to do is evaluate two integrals. The first integral, we're going to go from 0 to 1, 0 to b, pardon me, and we're going to let the limit b is going to go to 1 from the left. And the second one, we're going to look at a limit b going to 1 from the right, b to 3. It's going to be the same function here. Okay, so we just need to find an antiderivative of this. We could use a u substitution, but we don't really need to actually. So we're going to get, this is x minus 1 to the 2/3. So we're going to get 5/3 now. Okay, pardon me, we're going to have, let me rewrite it or I'm not going to be able to think about it. Limit as b goes to 1 from the left to b. This is x minus 1 to the negative 2/3 dx. The limit as b goes to 1 from the left. And we're going to have, okay, so we have, we add 1 and we get 1/3. We take the reciprocal, so we go 3x minus negative 1 to the 1/3 from 0 to b. So we get the limit as b goes to negative 1, sorry, to positive 1 from the left of 3, b minus 1 to the 1/3 minus, plug in a 0, 3, negative 1 to the 1/3. Now notice this is continuous at 1, so we can go ahead and plug in 1 here, and we're going to get a positive 3. Okay, so this area here is 3. Now let's take a look at this part. We're going to plug in from positive 1, and this time we have b to 3, so we should be a little careful here. We have the limit as b goes to 1 from the right now, and we're going to have the same antiderivative, 3x minus 1 to the 1/3, 0 to b, limit, b goes to 1 from the right, and now we're going to plug in b, so we have, I'm sorry, these are b to 3, these are backwards, b, 3, they come from these limits. Okay, so I have to plug in a 3 and then a b. So the first time I plug in a 3, I get 0. And I get, so 0 minus 3, b minus 1. I'm sorry, I don't get a 0. I don't know what I'm talking about there. Plug in a 3, and I get 3 minus 1 to the 1/3 minus 3, 1 minus 1, which is 0. Third. So here I get 3 times 2 to the 1/3 So my solution is going to be this integral here. I had to split up into two because we have that vertical discontinuity. Notice the limit existed in both cases. So the limit of the area to the left is finite. It converges. And the limit to the right is also finite. It converges. So the limit between on either side of this vertical asymptote is finite and converges. So the entire integral is finite and converges. And the entire integral is going to be 3 plus 2 times 2 to the 1/3 power. Okay, so anytime that we take this limit and the limit exists, that says it doesn't shoot off to infinity, it exists and is a finite number. Whenever that happens, we call it a convergent integral. Okay, last theorem. This is a very cool theorem. This is how it works. Suppose we have a proper integral, a proper meaning that a and b are both finite, there are no discontinuities, and let f be between 0 and g. Okay. So f is less than g for all x less than a. And we know that a to infinity of g of x converges. Then no matter what, if we let f go to infinity, it converges too. So basically this is what it's saying. Suppose I have some function, we'll call it f, okay, and we're going to let it go down here. We'll call it f, and on any particular region, any region at all, okay, from a to any value for b, anything up here, we know that the integral exists. Okay, we can find an integral. Now we're going to have a function g. I'll put g in blue here. Suppose that g is always, for every value of x, bigger than f, pardon me. So the blue is always bigger than the black there. Okay, this is g, and the black one here is f. Suppose that's the case. Then, if the improper integral from a all the way to infinity exists for g, then since g is always on top of f, then the improper integral from a to infinity of f also exists. Okay, and must be less than or equal to the original. So it's really just it's almost like a sandwich theorem for integrals. Okay, now here's a way we can use that theorem. Determine whether or not the following improper integral converges. Don't find the area, but find out if it converges. Okay, well, this is a little tricky because we don't know how to find an improper integral, an antiderivative for 1 over x cubed plus 1. We just don't have it. Okay, you can try many methods, but we don't know how to do that. We can, however, evaluate whether or not this thing converges. And here's how we do it. We look at this here and we say, can we find a function that's always bigger than it? Okay, well, if we have 1 over x cubed plus 1, then certainly 1 over x cubed is always going to be bigger. That's because x cubed plus 1 is larger than x cubed, and if we take the reciprocal, we flip the inequality. Right? X cubed plus 1 is bigger than x cubed, and anytime you take a reciprocal, it flips the inequality. Okay? So if this denominator is bigger than this denominator, that causes this fraction to be less than this fraction. Because of this, okay, we can look at this function from 1 to infinity, 1 over x cubed dx. But notice what this is. This is 1 over x to a power where 1 over x to p, where p is greater than 1. We know that this integral converges for any value of p greater than 1. So this converges. And since this holds for all x, this converges and is less than that. Okay? Done. That's our proof. Okay, we've determined that yes, indeed, this has finite area. This converges. And we didn't actually show what it is, but we showed that it must because this converges, or rather, this integral converges. Okay, that's a lot to take in. We're going to try to break that down in class tomorrow. All right, thanks, guys.